Thank you, everybody. Thank you for inviting me, and thank you for waking up early. I know that it's hard, especially now that we have a good weather outside. And so I'm going to talk about porphyrins with a specific configuration for volcanic reaction solar cells. But first, I want to do an advertisement because we are here in the Nanotech Congress talking about the present and the future of nanotechnology. And most of you are students, so I know that probably your parents are asking, why are you studying this career? Why are you studying these studies for the future, and it's not, you're not going to have work in Mexico? But that's not true, and you can prove it, and you can tell them that researchers, nanotechnology researchers, are creating big things. Actually, now in the market, there are more than 8,000 products in nanotechnology, developed by more than 2,000 companies in about 56 countries. So it's something that is now happening. And another important issue about the nanotechnology is that we are developing to achieve the specific development, sustainable development goals. So we can see here these goals that we really know, and we have to know because we have to work for this. First, Hungry Zero, health, education, water, energy, innovation in industry, sustainable communities, weather, and submarine and earth-like life. So we are working with nanotechnology to be applied in these areas. And now I'm going to speak specifically about energy. So the energy is a big challenge around the world. We know that a third of the world gas and greenhouse emissions are due to the energy. So it's something that we have to fix. We have to solve. And here we can see that China has the biggest emission in the world with 11,000 megatons. And United States has 6,000, and then we can see here Mexico, Spain, and Guatemala, that we have less emissions, but we have to work to keep it like that. And then we know that in the energy outlook of 2017, they figure out that for 2035, we will have an increasement of the renewable energy, but it will be always dominated by gas and coal and oil. But eventually this will be increasing the last 10 years. So these are the trends in energy. And we know that the solar technology is a good option. We have most of the time, we can see it. It's easy in our countries. So the solar technology has different kinds. So I'm going to focus specifically in photovoltaic. And I'm going to focus in these devices that, as you know, photovoltaics are these electrical devices that transform from the solar light to electricity by the photovoltaic effect. And we can see here that this is a picture of Guatemala, but I can imagine that here in Mexico I haven't seen, but I know that you have a lot. Yes? Okay. So, what we usually see is this silicon photovoltaic. That is the first generation that our colleague from Mexico was talking 2 days ago. So basically, in 2015, the capacity addition shares of photovoltaic in the world was China, the first with 30%, then Japan with 22%, the US with 15%, the UK and India. And then in the next 10 countries, we can see 2 countries from Latin America, which is super good. First, Chile, and then Honduras. But 2 years later, we can see that the same countries stay the first 5 countries with more capacity additions. During 2017, we can see that China increased to 54%. And then we have that in the rest of the world, in the next 6 countries, Brazil is adding some sharings for PV. So now, this graphic, you already know this graphic from our colleague 2 days ago. He showed different photovoltaic efficiencies. This is a a very good graphic because the National Renewable Energy Lab published every year an updated graphic with the solar cells efficiencies since 1975. So you can see here the first efficiencies, and then to 2018 how it has been evolved and in different kind of types of solar cells. So you can see that these are the higher PVs, but most of these are developing for some application by NASA or some space applications. They are very expensive, but they have good efficiencies. So now we are going to focus in the emerging photovoltaics, or known as third generation photovoltaics. So here we can see something very interesting. First, we can see the perovskites. I'm not going to talk about perovskites, but when you are talking about PV of third generation since maybe 4 years ago or 5 years ago, you cannot escape about talking about perovskites. Why? Because this is a generation, this is a PV very new from 2014 when I was studying my PhD in Spain. We were at the beginning in 2011 working with dye-sensitized solar cells. This was like the biggest top in the photovoltaics. Gratzel was publishing a lot of good efficiencies. Gratzel was the discoverer of this kind of cells. And he was even doing products with laptops with the screens of photovoltaics with dye-sensitized solar cells, and everything was super good. But in about 2014, people wasn't publishing about dye-sensitized solar cells, and not in good journals. Why? Because the photovoltaics had been evolved, then new discoveries had been done, and you can see here in 2014 how perovskites starts with the maximum of this emerging photovoltaics. So it changed everything in the photovoltaic world. So it changed everything for my lab too, but we stopped to do some molecules for dye-sensitized solar cells. We keep doing some organic solar cells because we see some potential in this organic in which are increasing. You can see that this is very good. So we keep betting for this kind of technology. And now it's changing again. Before, when I was doing the PhD from 2011 to 2017, we were working with these porphyrins as donor materials, and as acceptor we use fullerenes like PCBM 71 or PCBM 61. But now it's changing again, and what is more common is research about acceptors that are not fullerenes, other kind of acceptors. So that's what is doing my group now in Spain. Obviously, my director of thesis, Fernando Langa, he has a vision of what is the trending and what is better to research. So that's what is happening now. So I want to show you this news about October 4, 2018. This Arrechea is researching about perovskites, and they discovered how to do it as ink, as that was one of the things that was the cons about perovskites in comparison with other organic materials, because organic is easy to print. So now they are discovering new trends and things that can change again the photovoltaics. So now I'm going to focus on these organic photovoltaics in the bulk heterojunction solar cells, and to explain you how it works. It has 4 fundamental steps. First, the photoexcitation of the donor, as you can see here with this. So then we have an exciton, and this exciton has a diffusion between the donor and the acceptor interface. Then there is a dissociation between the bonds of the exciton, and then you can see an electron and a couple electron and a hole with this separation, and then free charge carrier transport and collect to the external electrodes. So that's the way that these photovoltaics work. And basically here is a mix of this donor material with acceptor material, so P semiconductor and N semiconductor. So now, the world record, basically here we have polymers with 12%, and you can see that now this is 2017 result, and they have developed another molecule as acceptor, not fullerene. Before we use fullerene. This is the record of 2016 with porphyrins, and this is the record with another kind of molecules. So we chose porphyrins because they have good properties for this kind of molecules. First, they have structural robustness, then thermal stability, they reach metal coordination. It's easy to do this chemistry. And then it has a strong aromaticity, absorption, emission, and as you can see, it matches with the solar spectrum. And it has two very typical bands for porphyrins, one P band and Q bands. So this P band is between 300 and 400 nanometers, and the Q bands around 5 to 600 nanometers. So then the main target was develop this kind of molecules, these porphyrins with different groups in the meso position and different bridge and different acceptors to be mixed with fullerenes in the main bulk heteroreaction solar cells. So we were using three different groups attached to the meso position to change the planarity of the photovoltaic, of the donor and the acceptor. So as in the literature, there is written that if it's more planar, it helps to have a better connection between the acceptor and the donor because it has more interface. So we tried with this very bulky group and with this more planar group to see what is the difference. And then we do another three change with the bridge. First, 1 TeV, that is the 3,4-diacetyl diaphragm, and then the 2 TeV, that is the dimer of the same molecule, and then another planar bridge. So we try with these three different bridges to know how it changed, how the current will change with this. And then we always use an acceptor to change the levels of HOMO and LUMO, because we have to figure out how to do it better in order to have a better match with the acceptor, in order to not be so far away, to have some recombinations or too close. So we change with these main no acceptors like the rhodanine and the ethylene. So here are the molecules. Finally, we have about 12 molecules with different structures, but always with the donor bridge acceptor and donor bridge acceptor in the other side. So basically, this is structure for the 12 molecules. Who is doing organic chemistry from here? Okay, so I'm not going to, I'm going to specify. So for people that is not working with organic chemistry, we do a lot of reactions. In general, we tell you we work hard with the lab, with the reactions, then with the purifications of the molecules, and then with the characterizations. We first started with the synthesis of the bridge named C1 and C2. So we do some reaction for monoformulate. We have to be careful of don't bisformulate this molecule, and then jodation. And then for the 2TB, we do a McMurray reaction. It's kind of difficult because we can here obtain the cis and the trans molecule, and we are interested in the trans molecule. And then we monoformulate by Wills-Mayer reaction, and then we jodate. We do the same process with the other connection, with the other bridge. And then to do the main donor or the base of the porphyrin, we start with a pyrrole and then with a dipyromethane, and then we form the porphyrin through a reaction very well known by Lindsay. They published a reaction in 1990 about a porphyrin with a 30% of efficiency. We only modified a little bit this reaction, obtaining 35%, and then we debromate, and by a Sonogashira reaction. It's a kind of difficult reaction because it has to be all through argon. We have to figure out don't have any oxygen in the reaction. And then we add this planar structure because we are interested in having it as planar as possible in order to see how it matches with the acceptor and how it changes the configuration. So basically it's the same procedure for the other molecules with the oxy, and then we can see here the match with the bridge by another Sonogashira reaction. I'm not going to get so deep in the organic because I'm going to bore everybody for those three that know about it. But you can talk with me later. So these are some pictures about the reactions, about the purification, about the molecule with some dichloromethane. And then of each new molecule, for the precursor, like the aldehyde and the main molecule, we do different characterizations. As we have seen in this congress, lots of people is working with different kind of characterization. For us as organic chemistry, we have to work with resonance, magnetic resonance of proton or carbon to be sure that we have that we are obtaining what we are saying. So it's like a puzzle here, and we have a spectrum of mass to see if it matches with the spectrum. Obviously, the infrared to know the groups, and it's very required for the journals, even if I don't like too much the infrared because it doesn't give me so much information as a nuclear magnetic resonance, but it helps a lot. And then we do a thermogravimetry. Here is very important to use the TGA because we can know the temperature of decomposition of these molecules. Because we are going to use it for photovoltaics, so we want to have a good value, a high temperature value. And most of it, molecules, has a temperature of decomposition around 350 Celsius, which is good for using in this kind of molecules. We do the DFT by Gaussian of all the molecules to know the structure. We do it wrong, I have to tell you the truth, because we do the molecule and then we do the structure and the theoretical calculation, but it has to be like in the other direction. Which as you have here, we have to match this theoretic and the practice in order to produce better research. And then here with the absorption, you can see that the porphyrin, without any bridge or without any acceptor, has this absorption, the P-band and the Q-bands characteristic of the porphyrin. But then when we add this bridge with the aldehyde, there is a shift to more like wavelengths, like the 400, it changed from 420 to 440. And then we can see that if we add an acceptor, there is a bigger shift in this absorption. So we can see that we are getting, in order to have a better current, a better matching with the solar spectrum. So that's what we see here, the solar spectrum and the porphyrin that we developed. This is only an example with one of the porphyrins. We can see here that it changed depending on the bridge that we are using, like the 1 TB or the 2 TB, so it changed the shift of and the enhancement of this absorption curve. And we do the electrochemistry to know the first oxidation, to calculate the HOMO and the LUMO through this oxidation and reduction. So we have here the band gap, that is the difference of the HOMO and the LUMO. You have heard about this before in another conference. And we're trying to make it match with the PCBM in order to have good properties to make this jump from the HOMO of the donor to the HOMO of the fullerene or the acceptor in this case. And then we have some image of AFM to see how it works, how the layer is in the mix of the porphyrins and the acceptor. And we can see here big domains, and it doesn't help to the efficiency of the device. And here we can see more like fibers, and it helps. But eventually, what we are doing now is adding some different additives, different chemistries, chemical components that can help to this interface, get a better interface. So our last publication in nanoscale, we developed a PCE of 7.63%. We have another of 8% with chlorobenzene. Adding chlorobenzene, it can change the efficiency of a device from 2 to 7. So it can increase a lot only adding another chemistry here. So what I want to show you is that the efficiency of the device depends on a lot of issues, not only the donor, it depends on the acceptor, it depends on the way that we are doing the mix of this nano layer between the donor and the acceptor. It changes depending on what are we adding or how are we going to do it. So in conclusions, we developed 12 new molecules of through organic chemistry for bulk heteroreaction solar cells. With porphyrins using rhodanine and moiety as acceptor and reach good current. I didn't show you, but our current is about 13 milliamperes per centimeters. And then, so we achieved a lot of publications with this work. As I told you, it was a work from 2011 to 2017. So now the group in Spain is working with another kind of acceptor, is working with another kind of molecules, and a group in Guatemala is working with them. Here is my acknowledgement to Fernando Langa, the group leader, Ana Arrechea, Pilar de la Cruz, and of course it's not achieved without without this collaboration with the Emilia Palomares from the Institut Catalan, and to Agustin Molina and Luis Echegoyen from El Paso, Texas, and of course my scholar from Fundación Carolina. And now in Guatemala, if you're asking what are we doing, we're collaborating with this group in Spain, but we are working in other nanomaterials focused and applying to construction. Why construction? Because we have funds from the construction industry in Guatemala. We had get some new projects from the National Secretariat of National Science. We got the first funds in 2016. And then last year we got another financial from CSIC Spain with a collaboration between two groups from the Institute of Construction, Eduardo Torroja, and Guatemala, and another group of the materials from Madrid. So we have some funds from them, and this year we got another funds from TUAS. If you don't know TUAS, I recommend you to look for this. It has good chance for our countries. They give different kind of funds. It's not a big amount, but it's enough to start. And you can ask for these funds in May of every year. They have like two different kinds, one individual grant and a group grant. In an individual grant, it's only one person who has to apply. In the group grant, you have to figure out how to match with 3 different doctors in order to get the grant. So we have this for develop novel materials with construction. We're working with 2 kinds, mortars with the dioxide titanium for these self-cleaning properties, and we are working with another nanotubes with different modification of organic modification to use it in cement for get a better mechanical resistance. So now that's what we are working, and I wanted to share it to you because as you see, the times change, and we have to, in order to look for the sustainable development goals, try to research something that is useful for our countries, try to research something that is going to get funds, because if not, we are not going to be able to work. So thank you so much for your attention, and if you have some doubts.
So we have time for questions.
I actually have two questions. The first one, you have mentioned that a planar configuration is better. But one of the problems of the planar configuration is that minority carriers should achieve the depletion zone where there is an electric field to be separated. So in this sense, sometimes it's better to use, when it comes to organic solar cells, the N region emission of the N region and P region, so that an electron hole that be created be easily achieve a depletion zone and be separated. But in your case, you say that a planar configuration could be better. This is the first question. And the second question was the band gap that you showed. In this case, the band gap was about 1.7, 1.8, which seems to be quite higher than the expected one from a good performance in a solar cells. Why is that? Why don't you reduce this value of band gap to increase your short current density? In fact, because the VOC is quite high, but the short current density is lower, and I think that it is due to the band gap in this case.
Okay, the first question is about the planarity of the molecular. So I was talking about the donor. So it changed a lot depending on how it is structured and how it's going to get these domains in the phase of the donor and the acceptor. So I'm just talking about the donor molecule, not about the interface between the donor and the acceptor. And then, so what is published, or what is the theoretical, with the experimental calculation, and what is published in the literature is that as much planar is the molecule, it's easier to get in contact with the acceptor, so it's easy to get the jump and have a better current. But here I want to show you that with this, that we expected to be one of the worst because it is very bulky, we have good results, but it was about the addition that we have this with chlorobenzene. So it changed the shape and it helped us. So it's very relative. It depends on everything. The donor, the acceptor, the interface, the additives, the way that you do even in the spin counter, it depends on how many times do you leave it, and how thin is the layer. So it depends on a lot of issues. And about the band gap, with porphyrins, this is a good current for porphyrins. Actually, in this kind of molecules, 13% is a good value. So what is the challenge with the porphyrins is the field factor. You can see that the field factor is about 63%. It can get, if you get a better field factor, actually the world record porphyrin has a 75 field factor. So it's like a limitation because we have to work with this structure.
Thank you.
Thank you, Susana. Nice talk. I'm wondering about the photostability of the porphyrin. The system.
Yeah, it's stable. It's stable. We have we did different proofs, and it's very stable. We have trying with I don't remember the time, but it's good. If it's with a coordination method.
And the thermal stability?
Yeah, it's about 300. The temperature of so the TGA is about 300, 350. So I don't know if you saw the graphic. Okay. So it's between 350 and 400 Celsius. So it's good. Yeah, for photovoltaic, it's enough good. Yeah.
Okay,
Thank you.
Questions? I have one. Usually, these systems are polythiophane with the whole carrier, because it's a polymer, goes everywhere, and the interfaces with the that electron donor very nicely. Now, I've seen that you use as a sequence some thiophene derivatives. Why not mention the two things? Why not disperse in porphyrins within the polythiophane and see what happens?
Actually, in a group, we were working with the small molecules because it was easy to fabricate for us. And in general, it's easy to fabricate more than a polymer, and it's more reproducible. But yes, how it works better is with these dimers or with this change of polymers. Actually, polymers is still having the record with bulk heterogeneous solar cells. It's not too much difference. It's about like 2%, like 15% is the record. But it works better. So the polymer works good. It has been some change between mixing porphyrins with dimers or porphyrins with polymers. So it's about play with these different roles, and it should be very interesting. I'm going to talk with the group in Spain to figure out how to mix it and do it. We have a collaboration in India. I didn't tell you, but Ganesh Sharma is the one that did this good mix of the porphyrins. I did a proof in Tarragona achieving 2% with my porphyrin, but this group in India did something amazing, adding different additives until achieve 8% that allow us to publish in nanoscale and other journals that before was impossible. Before we only published in dye-sensitized solar cells or dye pigments or these journals with less impact factor. So it's about playing, and it's a good option.
Well, since we have time, I may ask you something else now. Okay, we talked about the whole carrier, but you always use the fullerene derivatives, right?
For now, yes, but we are now in the group. We are researching different non-fullerene acceptors because that's what is working better. It has better results, and it achieves even the record with fullerenes very easily with non-fullerenes. So now people is working with non-fullerene acceptors. So it's now in 2011 to 2015 that we did the experimental part of this, we were working with fullerenes. But now they are trying the same donors with other non-fullerene acceptors, and it's working good. So it's the trends in this kind of photovoltaics is changing very fast.
Because I was about to suggest one thing. I'm a chemist. So you need a Reba series. You need a compound that has different center potentials. And there's fantastic compounds that do this. They actually gold metal clusters. And that could be a fantastic option instead of using fullerene. That's just a suggestion.
It's a good suggestion. We have to talk after.
Gold is expensive. Well,
Any more questions? If not, well, let's thank again our speaker. Okay, we're a big